Today we continue our discussion on relative ICs of planar linkages, and then we shall see how these relative instantaneous centers can be used for the purpose of velocity analysis of these linkages. To start with, let me take an example of the simplest 4R linkage. As we see in this figure, we have a 4R linkage, namely O2, A, B, O4. Because we have 4 links, there are n into n minus 1 by 2, that is 6 relative ICs. Let me list all these 6 relative ICs. They are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4. So our first task is to locate all these 6 relative instantaneous centers of this 4-link mechanism. Out of these 6, as I said in the last lecture, the location of 1, 2 is at O2, because link number 1 and link number 2 are connected by a revolute pair at O2. So O2 gives us the location of the relative instantaneous center 1, 2. Similarly, 2, 3 is at A, because for the same reason that links 2 and 3 are connected by a revolute pair at A. So A gives us the location of 2, 3. Following the same argument, we get 3, 4 at B and O4, 1, 4 at O4. So out of the total 6 number of relative instantaneous centers, 4 of these are located just by inspection. We have still to determine 2 more instantaneous centers, namely 1, 3 and 2, 4. To determine these 2, we invoke the Aronhold-Kennedy theorem of 3 centers. For example, if we say 3 rigid bodies, namely 1, 2 and 3 are in relative motion with respect to one another. Consequently, the 3 relative instantaneous centers, that is 1, 2, 2, 3 and 1, 3 will be collinear. Out of these 3, as we see, we have already determined 1, 2 and 2, 3. So 1, 3 must be on the line joining 1, 2 and 2, 3, that is the line joining O2A. This line O2A must contain the 3rd instantaneous center, namely 1, 3. Next, let us consider 3 rigid bodies, namely 1, 3 and 4 in relative motion. Consequently, the 3 relative instantaneous centers, that is 1, 3, 1, 4 and 3, 4 must be collinear. Out of these 3, we have already determined 1, 4, we have already determined 3, 4. So 1, 3 must be on the line joining these 2 relative instantaneous centers 1, 4 and 3, 4, that is 1, 3 also lies on the line OB. So we have said 1, 3 lies on the line O2A and also lies on the line O4B. As a result, 1, 3 lies at the intersection of these 2 lines when extended, that is here, and we locate 1, 3. Following the same principle, we can also determine the last one, that is this 2, 4. For this, we consider 3 rigid bodies 1, 2 and 4. As a result, 1, 2, 1, 4 and 2, 4 are collinear. 1, 2 is here at O2, 1, 4 is here at O4. So, 2, 4 must lie on the line joining O2 and O4. Then we can consider 3 rigid bodies, namely 2, 3 and 4. Consequently, Arnold-Kennedy theorem says 3 instantaneous centers 2, 3, 2, 4 and 3, 4 also are collinear. Out of these 3, we have already located 2, 3 at A, 3, 4 at B. So, 2, 4 must lie on the line joining A, B. As a result, 2, 4 is located at the intersection of the line O2, O4, that is the line joining 1, 2, 1, 4, and the line AB, that is the line joining 2, 3 and 3, 4. As a result, we get the location of 2, 4 at here, at the intersection of O2, O4 and AB. So, we determine some of the relative instantaneous centers just by inspection of the kinematic pairs, and the rest by application of Arnold-Kennedy theorem. Once we have determined all these 6 relative instantaneous centers, we are in a position to carry out the velocity analysis. To carry out the velocity analysis, let us look at this picture, this figure, where all the 6 relative instantaneous centers have been located as explained just now. For velocity analysis, let us say the angular velocity of the input link, say that of 2, is given. That means the problem is input angular velocity omega 2 given, and our task is to determine the angular velocity of the other 2 moving links, say link number 3, that is the line AB, and link number 4, that is the line O4B. So, at this particular configuration, if omega 2 is given, question is what is omega 3 and what is omega 4. Obviously, this will be true only for this particular configuration. To do that, we carry out the velocity analysis as follows. If omega 2 is given, then I can find the velocity of the point A, VA, which is omega 2 cross O2A. Since omega 2 is given and O2A is known, I can find the velocity vector VA from the input angular velocity. Now, A happens to be the relative instantaneous center 2, 3. That means, if I consider this point A to be a point on link 2, whatever its velocity, if I consider it to be a point on link 3, then it will have the same velocity. And now, let us consider the point A as a point on link 3, and link 3 is rotating at this instant about the point 1, 3. So, velocity of A, if I consider it to be a point on link 3, which is rotating with angular velocity omega 3 about the point 1, 3, that is, I have to take this vector from the point 1, 3 to A. Now, these two are same, these two equations both give VA, and the only unknown is omega 3. So, I can determine omega 3. To determine the, say, output angular velocity, that is omega 4, that is of the line O4B, we consider the point 2, 4, which we have already located. Now, 2, 4 is a point whose velocity will be same whether I consider it to be a point on body 2 or I consider it to be a point on body 4. If I consider 2, 4 to be a point on body 2 which is rotating about O2, so velocity of this point 2, 4, considering it to be a point on body 2 is omega 2 cross the vector O2 to the point 2, 4. Because link 2 is rotating about the point O2 which is 1, 2. As omega 2 is given, I can find out what is the velocity of this point. For counterclockwise velocity of link 2, it will be in this direction perpendicular to this line, and the magnitude I can find out. Now let me consider the same point 2, 4 as a point on body 4, and I must get the same velocity. So same equation I can write now, V24, considering it to be a point on link 4 is omega 4, and link 4 is rotating about 1, 4, that is O4, and so velocity will be the vector O4 to the point 2, 4. Now V24 is already known, only unknown is omega 4, so I can determine omega 4. So this is what we mean by velocity analysis of a linkage. If the input angular velocity is given, we obtain all the relative instantaneous centers and use them judiciously to determine all the unknown quantities. Suppose we are interested in finding the velocity of this particular point on link 3. We have already found omega 3. So, and link 3 is rotating about 1, 3. So, the velocity of this point will be omega 3 into, if I call this point P, velocity of the point P will be omega 3 cross the vector. The link 3 is rotating about the point 1, 3. So, 1, 3 to the point P, whatever this vector. Omega 3 is already known, this vector is known, so I can find the velocity of the point P. For example, in this particular problem, with omega 2 counterclockwise, the velocity of the point A is in this direction, perpendicular to O2A. And link 3 is rotating over this point, so omega 3 comes out as clockwise from this equation, these two equations. Omega 3 turns out as clockwise, so velocity of P will be in this direction, perpendicular to 1, 3 P, this vector, and in the clockwise direction. Now let me show you with a model that this 1, 3 and 2, 4, and in the model it will be also clear what is the significance of this relative instantaneous centers. Let us now consider this model of the 4R linkage. As we see, there are 3 moving links, namely this blue link, say link number 2, this gray link, that is the coupler, say link number 3, and this red link, that is the output link, say link number 4. So this is, according to our notation, O2, A, B, O4. Applying Aronhold-Kennedy's theorem, we have seen that 1, 3 is located at the point of intersection of these two lines, O2A and O4B. So these two lines intersect here, which I call 1, 3. Similarly, at the point of intersection of the two lines O2, O4 and AB, I get the instantaneous center 2, 4. So this is 1, 3 and this is 2, 4. Now if we move this linkage around this configuration, because this point is P1, 3, that means the link 3 is instantaneously rotating about this point does not move. This point has 0 velocity, as we will see when we see this move this linkage. you see all other points in this link 3 is moving around this configuration. This point has 0 velocity, is hardly moving. Now, to see the significance of 2, 4, let me consider this point a coincident point on link 2 and link 4. That means one point on link 2 and exactly just below this point a point on link 4. These 2 points on link 2 and link 4 at this instant have same velocity. That is why we call it 2, 4. And if we move this, you see this is the hole which was coincident with this P24. Right now this is a different configuration, so their location is elsewhere, but at that configuration this hole on link 4 and this point on hole on link 4 and the point on link 2 you cannot distinguish because they move with same velocity. Here you can see them distinctly. This is the hole which was coincident with this point at this configuration. So around this configuration these 2 points, one belonging to body 2 and the other belonging to body 4, move with same velocity. At this stage, let me carry out another example of a 6-link mechanism. Let us consider the model of this 6-link Whitworth quick return mechanism, which we have seen earlier. Here the input link is this link, this is O2A. This is the input link which rotates at constant speed, and consequently the output link, that is this tool holder, reciprocates along a straight line. Our job is, given this 6-link mechanism at a particular configuration, say this configuration, if first task is to locate all the relative instantaneous centers, then second step is, given the input angular velocity at this configuration, say omega 2 is given, what is the velocity of the cutting tool or this tool holder? That is the slider which will be our link number 6. So this is the problem that now we are going to solve. This is the kinematic diagram of the Whitworth quick return mechanism, the model of which we have just now seen. O2A is link number 2, which is the input link, that is hinged to this block 3, and the 3 is moving on the slotted lever 4, which is hinged at the point O4. Then link 4 is connected to link 5 by a revolute pair at the point B, and link 5 is connected to the tool holder, that is the link number 6 at the point C. So our first task is to obtain all the relative instantaneous centers. As we see, there are fixed link 1, 2, 3, 4, 5 and 6 links. So if there are 6 links, then the total number of relative instantaneous centers is 6 into 5 divided by 2, that is 15. So first of all, let me list all the 15 relative instantaneous centers, namely 1, 2, 1, 3, 1, 4, 1, 5 and 1, 6. Then 2, 3, 2, 4, 2, 5, 2, 6, 3, 4, 3, 5, 3, 6, 4, 5, 4, 6 and 5, 6. So this is the complete list of all the 15 relative instantaneous centers. At the second stage, let us now try to locate all those relative instantaneous centers which can be easily obtained by inspection of the kinematic pairs. For example, 1, 2 is easily located at the revolute pair between link 1 and link 2, that is at O2. Similarly, 2, 3 is easily located at the revolute pair connecting link number 2 and 3, that is at this point A. 1 4 is easily located at O4 because that is where the revolute pair between link 1 and link number 4 is. Link for number 4 and 5 are connected by a revolute pair at B, so 4 5 is at B. So let me try to write this. Here we have 1 2, here we have 1 4 at O4, at B we have 4 5, at A we have 2 3, next we have revolute pair between link number 5 and 6 at C, so that is 5 6. C is 5 6. Now we have located 1 2 3 4 5 revolute pairs and the corresponding 5 relative ICs. The other two kinematic pairs in this linkage is a prismatic pair between link 3 and 4 along this slotted lever. So the relative IC 3 4 will lie at infinity in a direction perpendicular to the direction of sliding, that is perpendicular to the line O4A. So I can draw a line which is perpendicular to O4A, and 3 4 lies on this line at infinity. We should remember that all parallel lines meet at infinity. So one can also say that if I draw a line which is parallel to this line, that 3 4 lies on this line as well, because these two lines are parallel and 3 4 lies at infinity and two parallel lines meet at infinity. So 3 4 lies also on this line. All parallel lines meet at infinity. So 3 4 at infinity, 3 4 at infinity on all these parallel lines. So we have located the relative IC 3 4. 6 is in perfect translation in the horizontal direction with respect to the fixed link 1. So 1 6 lies at infinity in a direction perpendicular to the horizontal, that is vertical. So if I draw a vertical line, all these vertical lines, I can write 1 6 at infinity along this vertical direction. So I have located 1 6. So because of the 7 kinematic pairs, we have just by inspection located 7 out of these 15 relative instantaneous centers. Rest 8 can be determined only by invoking Aronhold-Kennedy theorem. But because there are so many numbers, it will be quite confusing if we do it haphazardly. It is better to do it a little more systematically. To do it systematically, I put these link numbers 1, 2, 3, 4, 5 and 6 at equal spacing on the circumference of a circle. This diagram is in fact called a circle diagram. Here links are represented by these numbers 1, 2, 3, 4, 5, 6. And if this relative instantaneous center 1, 2 has already been determined, then I join 1 and 2 by a straight line 1, 2. This line represents the relative instantaneous centers 1, 2. And if the line has been drawn, that means this has already been located. So let us draw all these 7 relative instantaneous centers that we have already determined. We have determined 1, 4. So I join 1 and 4. I have determined 1, 6, so I join 1 and 6, 2, 3, so I join 2, 3, 3, 4, so I join 3, 4, 4, 5, and 5, 6. So, corresponding to the 7 relative ICs which have already been obtained by mere inspection of the kinematic pairs, I join these 7 lines. Now, to apply Aronhold-Kennedy theorem systematically, we should consider a quadrilateral in this figure. For example, I have already completed 2 quadrilaterals, namely 1, 2, 3, 4. All the 4 sides are known. Then the diagonals of this quadrilateral can be decided at the second stage. For example, I can determine, say, this diagonal (1, 3). How is as follows? We consider that 1, 2, 2, 3, and 1, 3 are collinear. We have already drawn 1, 2, and 2, 3. So, 1, 3 must be lying on this line. This is what we call the Aronhold-Kennedy theorem, that 1, 2, 2, 3, 1, 3 are collinear, 1, 2 is here, 2, 3 is there. So, 1, 3 must lie on this line. And 1, 3 this diagonal, as I see, 1, 4 and 3, 4. So, I consider 1, 4, 3, 4 and 1, 3. We have already determined 1, 4 here, and 3, 4 is on this line at infinity. So, 1, 3 must be on this line as well, and 1, 3 must be on this line as well. So, the point of intersection of these 2 lines gives me the location of relative IC 1, 3. Same way, I can determine 2, 4. 2, 4 I can consider as lying on a line joining 2, 3 and 3, 4, and also on the line joining 1, 2 and 1, 4. This is 1, 2, this is 1, 4. So, 2, 4 must lie on this line. And 2, 3 is here, 3, 4 is here. So, it must lie on that line. That means the intersection of this vertical line which contains 1, 2 and 1, 4, and this line which contains 2, 3 and 3, 4 determines the relative instantaneous center 2, 4. This process can be continued like considering this quadrilateral whose sides have already been determined. In the next step, we can consider the 2 diagonals, that is 4, 6 and 1, 5. So, we have also determined 1, 3 in the second step. So, let me put a cross. In the second step, I have determined 1, 3 and 2, 4. And in this step, I can consider 1, 4 and 4, 5 and 1, 5 are on one line. 1, 4, 4, 5, 1, 5 is on one line, and also 1, 6, 5, 6 and 1, 5 on one line. As we see, this is 5, 6 and 1, 6 is on the vertical line. So, 1, 5 must lie on this line. 1, 5 must lie on this vertical line. And also 1, 4 is here, 4, 5 is here. So, 1, 5 must lie on the line joining O4B. So, if I extend this line, at this intersection of these 2 lines, I can get 1, 5. Now, after the second step, we see lot of quadrilaterals have been filled up. For example, now I can determine 2, 6 because I know 1, 2 and 1, 6, and I also know 4, 6 and 2, 4. Then in the third step, I can determine the rest of the unknowns relative ICs like 2, 6, 2, 5, 3, 5 and so on. The diagram will become very complicated. I will show the complete diagram where all the relative instantaneous centers have been located following the same procedure. Following the procedure just now explained, finally we obtain all the relative instantaneous centers of this 6-link mechanism as shown in this figure. We note O2, that is 1, 2, A, which was 2, 3, B, which was 4, 5, C, which was 5, 6, and O4, that was 1, 4. These are the 5 R pairs. Immediately locate 5 relative instantaneous centers. Corresponding to the prismatic pair between 3 and 4 along this O4A, we have 3, 4 in a direction perpendicular to O4A and lying at infinity. So, all these parallel lines 3, 4 lie at infinity along this direction. Similarly, 6 is in horizontal translation with respect to link 1. So, link relative instantaneous center IC 1, 6 is at infinity in the vertical direction. That is, on all vertical lines I can say 1, 6 lies at infinity. Following the procedure we just discussed, we locate all the rest of the relative instantaneous centers like 1, 3, 2, 4, 1, 5, 4, 6, 3, 5, 3, 6, 2, 5 and 2, 6. After obtaining all the relative instantaneous centers, we are in a position to carry out the velocity analysis of this mechanism. That means, for this configuration, if one prescribes the input angular velocity omega 2, which is given, and we have to determine what is the velocity of the cutting tool, that is link number 6. What is the velocity of link 6 or velocity of the point C, which is same as the sliding velocity of the cutting tool. Now, to determine this, we argue it out as follows. Let us consider this relative instantaneous center 2, 6, which is lying here. Now, by definition, this point, the velocity of this point, if I consider it to be a point on body 2 or if I consider it to be a point on body 6, it must be same. That is the definition of relative instantaneous center 2, 6. Because omega 2 is prescribed, I can find out the velocity of this point 2, 6 velocity say of the point 2, 6 is, if I consider it to be a point on body 2, it is omega 2 cross body 2 is rotating about O2, that is here O2 up to the point 2, 6, this vector. So, we can find out the velocity of this point 2, 6 by considering it to be a point belonging to body 2. Omega 2 is given, link number 2 is rotating about 1, 2 and this point 2, 6 is here. So, I get the velocity. If omega 2 is counterclockwise, the velocity of this point 2, 6 is horizontal and to the left because this line is vertical. So, I get the velocity of this point 2, 6 is along horizontal direction and towards left, and the magnitude is omega 2 into this distance O2 into 2, 6. Now, let me consider now the point 2, 6 as a point on link 6, and it must have the same velocity. And link 6 is a slider. That means it is in perfect translation, in pure translation, which means all points on link 6 must have the same velocity. So, V6, V of the body 6 is same as V26, because all points on link 6 have the same velocity. So, immediately you get the output velocity V6. So, in today's lecture, we have seen how to determine all the relative instantaneous centers of a planar linkages by considering the different kinds of kinematic pairs and by successively applying Aronhold-Kennedy theorem of 3 centers. This method is definitely going to give you result so long you have not more than 6 links in a mechanism, which is sufficient for the purpose of this course. So, for a 6-link mechanism, there are 15 relative instantaneous centers, and all of which can be determined. Once we have determined all the relative instantaneous centers, I have also explained how we can use the location of these relative instantaneous centers for the purpose of velocity analysis. That is, given the input velocity, we can find the velocity characteristics of all other links present in the mechanism. One thing we can remember, in the last example we saw that the output link was a slider. So, the velocity of all the points of a slider is same because it is in pure translation. That fact was very cleverly utilized to find out the output velocity when the input velocity was prescribed.